Welcome to our video on the engine management using the IPO process. We're going to be talking about inputs. We're going to be talking about how the computer processes information and outputs it to the car. It gives you a handle how the system works and allows you a little bit better diagnostic procedures. Okay, in our class on engine management using the IPO process, input, processing, and output, we're going to go over and look at some class objectives. First of all, we have to learn the different engine management systems out there. We have to learn the input and the process output operation of the systems we're working on the computer. We have to recognize the main sensor inputs, the main actuator outputs, and discuss the types of engine management systems that are out in the cars today. Okay, if you look at our screen, we have the inputs, the processor, and the outputs. If you look at the bottom of the screen, those are the inputs. Now, this is an older, like 1990s car. So what you're going to see is not a lot of inputs on the particular system. As we go up to our processor, that's the PCM is going to take the process. Again, if it's analog, it has to be converted to digital because computer only does the ones and twos, ones and zeros, excuse me. And if you go up the top up there, you will see the output. So again, this is the way some people were drawing the wiring diagram or giving you a schematic so you can understand that the inputs are there. You also understand by looking at information, some of the inputs are sharing grounds or sharing voltage up there so they can affect another sensor. This is a really easy way of looking at it, and I loved, when I was training for this particular company, I love using these charts. Now the next slide is what we're going to be talking about in this class. You have inputs. They're going to be sensors. Are they going to be switches? So we have a brake switch. We're going to have other components on the car we need to look at. Now this is unprocessed data. This is raw data that's going to be put into the computer. Again, if it's analog data, it's going to be converted to digital. If it's digital data, a switch would be digital information, all right? And if we go to the process into the system, ECM up there. Now, when that goes out of the system, it's going to come out in a digital format. So we're going to have outputs where we turn something on or turn something off. We have an actuator, like an injector would be an actuator. A solenoid where you would turn it on or turn it off. Or you would duty cycle it. That's another thing we do, or pulse width management on systems. We're going to have relays that we're going to turn on and off, or duty cycle relay at times. We have motors that are going to be turned off. Again, think about your fuel pump is actually a motor. So we're going to turn that one and make sure that it works properly. And we might duty cycle that fuel pump, or we might do other things with it. And we might change it when frequency, kick at a certain range. The other thing you're going to look at is we have to bring all this information, and we have diagnostics built into the computer. One other thing to keep in mind is we actually have two processes going on in most cars. We have OBD2 and they have an enhanced side. OBD2 is for emissions, and the enhanced side is for more drivability, comfort, and whatever else is going on in the vehicle. Now that's processed data. What most of us forget is the data coming out of your Scantool, which is from your PCM, is processed. So that information is interpreted data of what it sees. There are times when you might have a sensor that is reading incorrectly, and the process will give you the information telling you it's wrong, or sometimes it will substitute a value on particular vehicles. Will not do that in OBD2, but it will do that in an enhanced side. It will substitute a value, thinking that this will make the car run better. So that's what we're looking at, the IPO process. Keep in mind that we have to have sensors on one side, go to the computer in the middle, and we have our outputs on the other side of this circuit. So we're looking at data that we can look at, diagnose with the car. Now, I'm going to go over and do a little bit of a live, tell you one other thing we have to talk about next. If we go over to, I do European up here, I'm doing the OBD2, and we get it up here. One thing you have to realize when you go OBD2, there are another thing that's kicking out. You have languages. So it's loading up the system, and what it's going to do is going to go out and check if it's a CAN bus system, or it will stop wherever it looks at. So if you look at 1850, J1850 variable pulse width modulated, I have keyword, I have a fast process, and once it finds what it was, J1850, it will automatically come up. On this particular vehicle, it gave me the VIN number. You won't always get that with all cars, but it tells me my mill light is off. It says no codes up there. It tells me my readiness stuff. So what I was trying to tell you is that they talk certain languages. So if you were on a canned vehicle, it will be at a certain speed, a lot faster. A J1850 might be a lot slower. J1850 can be on Ford and it can be on General Motors. On General Motors, it uses 1 wire. And on Ford, it uses 2. So you look at a different process. 2 for General Motors and 2 and 10 for Ford. So you're looking at data that's up there. So you want to make sure you get the proper operating protocol so you can talk to the car. Okay, when we're looking at information on the engine management system, I'm just going to call it EMS, there are different types of systems out there on the market. Chrysler has done speed density since the beginning. Some of the imports that Chrysler brought in maybe do something else. But speed density, we're going to use the map sensor as a primary sensor in the system. It's going to be measuring manifold absolute pressure. That is not vacuum, that's manifold absolute pressure. We also have mass airflow sensor, which is predominantly on a lot of vehicles out there. Predominantly on General Motors. General Motors at one time was speed density, and they switched back to MAF. So the MAF is the mass airflow sensor, is a primary tool for measuring the airflow going in the engine, and that's how we're going to determine our outputs in the process. Then there's a thing called Dyna-Air. Dyna-Air is used on some vehicles a lot nowadays, especially it started on General Motors, where they would use the mass airflow sensor and the map sensor. We're going to talk about that. And since 2008, all the vehicles in the United States switched over the CAN data bus. And the other thing they did at the same time, they went over to what's torque-based engine management, which means that we are using the throttle body is going to be mechanically done. We're going to use it in the process. We have a throttle body and we have an accelerator pedal sensor. The accelerator pedal sensor is sending signals to the computer, which is going to open or close the throttle as needed. So we got a whole bunch of things going on. Now, speed density. We have to talk about this right off the bat because a lot of people, and this is even something that I want to make sure you understand. First of all, speed density systems measure the pressure, not vacuum, but the pressure after the throttle body, all right? The mass airflow sensor is before the throttle body, and it can be vane airflow sensor, it can be a mass airflow sensor in different types, it can be heated wire, it can be heated film, whatever we're looking at. So that's a big difference. Now, there's a misnomer out here. A lot of people says it's measured vacuum. There is pressure in the intake manifold at all times. Whenever intake manifold is open, wide open throttle, you get atmospheric pressure in it. But as the valves are opening and closing, you're going to see pulses inside the intake manifold, and that's why we do have pressure. That's why you're looking at manifold absolute pressure might read 8 inches of vacuum, and if we have a barometric pressure, our barrel sensor says 28. We now know we subtract the 8 from the 28, and now we know we have 20 inches of vacuum intake manifold, but 8 inches of pressure. So it's something to keep in mind if you're doing your diagnosis. Speed density. It's one thing I want to make sure you understand. Speed density has a lot of inputs, calculated, everything's calculated. So we're looking at, we have the manifold absolute pressure up there in the black, we have the throttle opening, and needs to know where that's at. We have to know what the intake air temp sensor is, we have to know what the coolant temp sensor is, we have the input up there. The computer has some kind of setup remedy inside that tells you volumetric efficiency, that's built into the computer, but we'll talk about a little bit more. And it has to know if the EGR is being turned on and off. For you guys that's starting to get into looking at this, if the EGR is not working correctly, it will cause a problem on the particular car, because what they do is when the EGR comes on, it's going to change the air-fuel mixture. They're going to back off the fuel trim on the vehicle at that point. So a lot of times EGR can cause an issue on these particular cars. Let's go over and look at this calculation. This is one of the older ones. They have another calculation up here, and I love using calculations for 2 reasons. The first of all is RPM divided by max RPM times the map. What is that divided by? The barrel. In other words, they're always using their barrel sensor. That's your key on, engine off test on the map sensor itself. Then the next one, that's the load. The next one is base pulse width calculation. So we're doing load on that part. We're doing base pulse width calculation. Is a throttle position sensor times the engine coolant temp sensor times the inlet air temp sensor times this is a critical one, sense battery B+. So it has to know what the battery is. All these systems have to know what the charging voltage is. If it's not correct, they're going to have a problem. On a mass airflow sensor, if the battery voltage or the charging voltage goes down, they automatically increase the injector pulse width to compensate for it. So that's something to keep in mind. The last one up there, it says times LT. Well, LT is long-term fuel trim. So keep this in mind, long-term fuel trim is learned. It's always in memory, no matter where you go in the vehicle, it's there. So if you look down below, it says after long-term fuel trim is stored in memory, it's part of the base pulse width calculations, all temperatures, either hot or cold, or open or closed loop. So that is something you always got to keep in mind. Always look at long-term fuel trim and see if there's a correction on the car. Do this on mass airflow sensor cars, do this on any car, the long-term fuel trim's there. Now I'm not done yet on my base pulse calculation there. The next thing I'm going to have to multiply that time is the O2 sensor voltage. They usually use a switching style O2 sensor. A switching style O2 sensor is where it goes under 200 millivolts and go above 800 millivolts. It cannot actually tell you the actual air-fuel ratio. It just tells you whether it's running rich if the voltage is high or lean if the voltage is low. That's all it can tell you. And it should average around 450 to 500 millivolts. General Motors 450, I think Ford's like 461, and I think if most of the time on a Chrysler is around 500 millivolts or in the process. The next one, that's all calculated, and now we have the pulse width to the injectors. A lot of calculations here. Chrysler is one of the best companies for doing this when a lot of people don't like Chrysler, but they've been at this a long time and they've got it down. Now they have the thing that you might want to look at, it's called T-MAP, which is the throttle and the map sensor together to get a quicker response on the car. So there's a lot of things that's going on. The map sensor, again, it's the highest priority in the system. Now, again, what I wanted to show you here is we have high atmospheric pressure, 14.7, 14, depending on your altitude. You always lose about 1 inch per 1,000 feet, okay? So you have the restriction. Anytime you have a restriction, you will keep the flow down, you restrict the flow, you will create a vacuum on the other side of the restriction. The restriction we're looking at is the throttle plate itself. So before that, we have 14.7 PSI around where I'm at, and after that, we have less pressure, but we have what we normally would call negative pressure or vacuum. So you want to make sure, as the piston's going down, we're creating expansion there, we're creating a negative pressure in the system. Now, I like doing this a little bit different on the mass airflow sensors. The mass airflow sensor system out there, the EMS, most of the time it's a mass airflow sensor that's there, but you also have a little correction for the intake air temp sensor. So that's something else you have to look at. So I always look at those two together. And if you ever notice, most mass airflow sensor has an intake air temp sensor built into it. So again, we have an air sensing passage, and depending on the mass airflow sensor you got, it could be a hot wire, it could be the film, or the old ones would be a vane airflow, but they would actually be able to tell you the airflow going through the car. Now, we don't need a lot of correction on this because of the heat and the process, but this is a real good idea of the setup. Now, the next one up here, General Motors came out with this first. So General Motors uses a mass airflow sensor calculation. I've heard both ways, so keep this in mind. They will switch systems to determine what's going on in the vehicle. So if the throttle's steady, you're probably going to use the mass airflow sensor. With the rapid throttle changes on it, you're going to switch over to the map sensor. So they're going to use two together in a calculation to get a better idea of the load and what's going on with the vehicle. Even other car companies have gone to this. So if I look at a couple up here, I got a GM example up here, and you're going to look at some of the information there, guys. You've got intake air temp, and you got the map also. And you also have what else up there? Mass airflow sensor. These are both used. So if I go over to a Ford, Ford is predominantly a mass airflow system, but if you look at what we got up here, I have the map sensor, I have the airflow sensor, and I have the throttle position sensor. This is what you would probably be looking at, key on, engine off. But if you look at my temperatures above 100, this would be a warm engine. If we're doing a lot of a diagnosis, we want to make sure the car has been sitting for at least 8 hours and it's cold, so the intake air temp sensor. and the coolant temp sensor within 10 degrees of each other. But I wanted to show you that we do have that process on this particular vehicle. Now, again, what have we got? Airflow, mass airflow sensor, and we have the map sensor. So this one has both. This is a 2012 Ford Fusion. This one also, if you notice real carefully, it has a battery voltage up there, and the battery voltage is only running about 11.94. This particular vehicle needed a battery, and it had some issues on it, so that's what we did. This is my torque-based engine management system. There are two versions of this. One of them has electronic throttle control module, and the rest of it goes right through the computer itself. So we have the throttle pedal position sensor, or we're going to call it absolute pedal position sensor. That is the sensor data that are going to come in with the pedal on it, and then we also have the ability to send that out to the VCM. It calculates what it thinks it does, and it opens up the throttle and relationship. That's what's been going on with torque-based engine management. And you're going to see they have different PIDs up here. Not all Scantools will give you this information. So I go out and picked a few that would. So on this particular vehicle right now, if you look in the areas where I have the boxes on there, you're going to see that I have the torque readings on this particular vehicle. So you keep in mind, torque-based engine management is going to be on most vehicles up there. So I'm looking at this again. Let's look at the process up there. Blew it up just a little bit, and you're going to see that we have torque-based being on the vehicle, and that's how it's going to control. They are monitoring the system and give the proper torque to the vehicle. And that works in conjunction with your ABS system, your traction control system, and a couple other components on the vehicle. Some nice little information. The other thing is, all that data that we're sending in is raw data. It has to be converted over. And then the next thing it's going to be doing is there are tables, or processing boxes, whatever you want to call them. I heard one guy says it's like what you would call storage containers with boxes that you might want to see. However you want to look at this is up to. Storage cabinet in your shop where you have drawers. It might be different drawers as you go up and down. All this is different ways you look at it. So there are tables here. And the tables are how they're going to take the information based on load and RPM and temperature on how they're going to control the fuel into this engine or the timing to this engine. There's quite a few things it does. Now the next one up here, like I said, long-term fuel trim is learned in cells. I did a dry cycle on this particular vehicle. It's a Scantool I picked up for this particular reason. I think two Scantools to do this would be the eScan out there with their generic OBD2 Scantool will do this. This one is from the HP tuners. I like this one because it gives me my data like this. So I could see all the graphs. I went and did a road test on a particular vehicle and brought it back. So somewhere about 2,400 RPM and a different map sensor at 40 kilopascals absolute, I was at minus 11. So this vehicle was pulling fuel away all during the line. So the car is running slightly rich. Nothing that caused me any problems, but it's there. So the idea is here, you can go out and grab this information and look at it. They would take this if I was programming or reflashing or tuning a vehicle, I would be able to take this data and put it back into the computer, let them understand what's going on. So there's a lot of tables the computer does. That's why I wanted you to see this. So that's what's going on there. Now, I have one more thing to look at. If we go input and output, we have sensors and actuators. I showed you a minor chart before. Now you're looking at a large information that's going on. There are primary inputs for the car to run, but nowadays we have so many sensors on the vehicle. We can have over 100 sensors on some systems, and we have a whole bunch of computers. So we're looking at a lot of information to process. Keep this in mind. You have to understand the sensor inputs related to what you're looking for. So fuel trim would be what? Mass airflow sensor, map sensor, throttle position sensor, intake and coolant sensors. And you would be able to look at what you would have a problem with. You have to understand there are sensors that will be related just to that code or whatever you're looking at. So again, if you were looking at code criteria on a particular code, it would tell you what sensors are related to the issues that you might have. So you might want to check those in conjunction. There's a lot of information out here. We're just going to kind of break it down to make it a little bit easier to understand, and we go to the next process. When we're using this particular tool, remember I told you about torque. torque engine management. It's been around for years, but we haven't really done as much as we should for it. So I want to go to the Scantool right now, and if you look, it says torque delivered signal, if equipped, 87.843. Notice it says inactive. That's something else that you want to start looking at on your cars. Look for the torque figures on there and start getting a database that you're going to use for later on, because it's been around since 2008 and most of us haven't been using it. Now I'm going to go back to the data stream on this particular bar, and I was using engine data too. So if I'm looking at, there's cranks, notice this one, it says torque request signal if equipped. So I've got 3 there. I'm going to go back up again. There's engine life remaining. That isn't, again, what you look at, injector pulse width. Let's just look at those 3 and see what we get on this particular vehicle. All right, so now I look at, I've got torque request, I've got the torque delivered signal, and if I'm a little bit high or a little bit low because I want 0.5 and I got 87.43, so in other words, I've got more than I need. So this is something you're going to start looking at because it's based on the throttle angle plus the accelerator pedal plus the conditions of the car. Something to start looking at and going across. Not a lot of people are talking about this, but it's something we need to start addressing with our techs. And I'm going to have more somewhere down the line on this as we go across, but something else to look at. Just thought I'd pass it along to you. Let's look at something else. Okay, there are 6 primary inputs that you're going to have to deal with on all cars. It doesn't make a difference if it's a 1990 or a new one. There's 6 main ones you're going to have to look at for the car to operate and go down the road and do some jobs. So we're looking at the first 2 up there are for temperature. So we have to know the coolant temperature and the intake air temp sensor. That makes a really good combination. They should be on a key on, engine off car. It's been sitting overnight. They should be within 10 degrees of each other. And that gives you an idea that you're a good start. The coolant temp sensor has got more influence than the inlet air temp sensor, but you have to have both to do the good job for understanding. The next one down is number 3. Number 3 is called load. That can be your manifold absolute pressure sensor, your mass airflow sensor. I've got the barrel up there because the barrel there is key on, engine off, what it should be reading. That's a real important thing to use. So those are the load sensors, how it determines. If you saw what we did before, the load section was showing you all the sensors we needed. The other thing is RPM, and you have to have throttle position. Now, on some of the newer cars, I have become thinking that you can use a throttle position sensor as a load sensor, but on older vehicles, not as much. So keep this in mind when you're doing it. And the last thing up there is oxygen sensor or air-fuel ratio sensors. Now, if I switch over to the computer over here and look at it, I have hooked up this system. And if you look at my absolute throttle position sensor is at 0. My mass airflow sensor right now is 6.53. This is a demonstrator or what we call a training aid. So I want to make sure you understand that when you hit the button there, it comes up and it says grams per second, pounds per hour, or pounds per second. Some of your scan tools you're working on will actually go to pounds per hour, pounds per second, and that will mess you up when you're reading. So you understand that some of them will cross over and change. So on this one, I'm leaving it grams per second, so that leaves there. The other thing is the coolant's going to be in Fahrenheit. I could put there's no mark down there, I can't change it. It's going to stay Fahrenheit. RPM is there, and down at the bottom it's intake manifold pressure. On the intake manifold pressure is 13.2. On this particular unit, if I push the button there, it goes to megapascals absolute. Some of them will switch from PSI to inches of mercury, either way you look at it. Now, if I wanted to know what the barrel sensor was reading up there, and I listened to my local weather station, you're better off listening to the local airport to get a good reading, I would want to know what the inches of mercury would be. So, rule of thumb, 2. So I take and multiply this times 13.2 times 2, that would be 26.4. That would mean I'd be at a higher altitude where I'm from. That would be up. Remember I said 1 inch you lose 1 inch per 1,000 feet, so that's there. So if we look at a process, now that's just to get me started. Then to get some more fine tune on it, I might want to use my O2 sensor. These are the 6 main inputs you're going to be looking at for a vehicle. So it's a really good idea to set your Scantool up on a car that's got some problems, or if you're a student and you're starting to learn this stuff, you want to be able to look at the main inputs and see how they interrelate to each other to get a good idea what's going on with the vehicle. All right, if we look at our primary sensor inputs, the RPM, the crankshaft sensor, and the camshaft sensor are there to use. The RPM sensor is used to trigger the injector pulse width and other functions up there. It's used for, if accelerations, it's going to be used if we're going to do timing changes on the particular car. Also, it's the same process. Now, input can be a crankshaft sensor or a combination of crankshaft sensor and a camshaft sensor. A lot of times when we went to sequential fuel injection, we went to having to have a camshaft sensor. There are some vehicles that just had a camshaft sensor, believe it or not, and that's it. So there's some things we need to look at. If the RPM sensor is missing, we're probably going to have a no start. If the RPM is erratic and the signal is not correct, we'll have a problem. It's always a good idea to look at timing in relationship to RPM. If you rev it up, they should change. If you change the load on the vehicle, the timing should change and the crankshaft sensor should always increase with speed. I've had times where a couple of cars it didn't, so there's an issue where we had a module that was defective. Now, if we go over to our next slide, where we're looking at the barrel, the map, and the MAF sensor. These are all load sensors. And the map and the barrel should be the same at key on, engine off. Then one other thing I want to make sure everybody understands, that on some particular cars like Chryslers, you might have a problem with it when you let the key shut off. Depending on how you did it, it might trap pressure inside the map sensor at that point. I'm going to call it trap, but it'll have an inch or two there. What you want to do is do a barrel update. A barrel update is doing a wide open throttle. The barrel always updates at key on, engine off, and wide open throttle. And so if I do wide open throttle, it should update the information drastically. The other thing you can use this for, I just throw this in, if you have a car that has a map that's being used as the barrel also, you can also go down the road and put your foot flat into it and watch the barrel PID. When you look at the barrel PID, it should automatically update. When it goes down the road, it should be the same as key on, engine off, or slightly higher. If it goes down, you have a restriction on the intake side of the particular car, and that gives you an idea where you might want to look for your possible problem. The one I had not too awfully long ago was the air filter hadn't been changed in like 15 to 20,000 miles, and it affected the readings on my particular car. So again, the key on engine reading used for the engine startup, fuel injection, and the fuel injection on a key startup with a cold engine will be higher, and then it will come down slowly to compensate for it. You're also looking at for the running pulse width and timing corrections on the car. The map sensor also can be used for the EGR, determine if the EGR is working properly. Normal readings, what I see is somewhere between, I've seen 0.9 to 1.5 at idle, in that range, and with 18 to 21 inches of vacuum in the particular vehicle. So another way to look at it would be 8 to 12 inches of manifold absolute pressure at idle would compensate and give you the same kind of readings. Now, if I move over to the mass airflow sensor, just talking about it, I want to make sure you understand that it will give you the timing and fuel curves, just like we just said. The other thing is, on some vehicles, there is no map sensor or barrel sensor in the car, so the mass airflow sensor becomes that. On older Fords, we had that issue for quite a while, where it would have learned off the map, it would come up with a barrel PID, so keep that in mind. Readings at idle should run 3 to 7 grams per second. You always see that. My quick tip is 1 gram per liter of displacement at idle, minimum. So if I have a 2-liter engine, I need to be above 2. There might be slight exceptions to that rule. The only exceptions to that rule would be Kia and Hyundai might be slightly lower. That's the ones I run into. But a good key would be 1 gram per liter of displacement at idle, and you want to make sure it's working properly. And as we said before, you want to make sure you use grams per second for the most part. As we saw with this Scantool here, Make sure you got the proper readings when you're going forward. Coolant temp. Coolant temp is going to come out. It's going to give you the base pulse width when you first start up on a cold engine and the ignition timing curves on a cold engine. As you warm up, it will go to a different table, a different setting as the temperatures are there. The emission control devices are also controlled by this. On a cold engine, it's not going to allow certain things to work at idle speed. As it warms up, it will allow emissions devices to work on there. And again, cold start, the CTS and the IAT, coolant temp sensor and inlet air temp sensor should be within 10 degrees of each other. Now, keeping this in mind, this has more control than the inlet air temp sensor does. So keep that in mind when you're doing your diagnosis on the particular vehicle. And some of these are going to have a negative thermal coefficient. Some of them are going to have a dual path depending on a particular year. So they'll switch at about 120 degrees on some of them. I think that's correct. But it'll switch to go down the process. They call it dual path, where they switch a resistor in. Inlet air temp sensor. It is a fine-tuned sensor. Its input to fine-tune the fuel injection pulse width, the timing, and the idle speed settings. Again, if the car is running cold, it will change the settings slightly. It doesn't have as much adaptation off of it, but it's still there, and you need to check this. I've seen times where inlet air temp sensor caused me a problem. I had one time that an evap system would not work, and the only problem was the inlet air temp sensor had some debris on it, and when I cleaned the inlet air temp sensor, put it back in the vehicle, my evap monitor run right immediately after that. Throttle position sensors. Now we have throttle position sensors that are not at the throttle, they're at the accelerator pedal. I call them accelerator pedal sensors, but your throttle position sensor is the one that's either at, we're looking at the throttle body itself. It's used for injector pulse width calculation, ignition calculations. It's also used for AC, wide open throttle. If I go wide open throttle and throttle position sensor, it will turn the AC off. Some emission control devices will not work at idle, but they will work at off idle, like your purge solenoid on some vehicles. And the sensors, I call it the on-demand sensor, because what you do is you put your foot into the floor, you put the demand on the vehicle. Or you change the torque requirements for that vehicle by putting your foot. So you're looking at some really good information to use. And the last one we got up here we're going to look at is O2 sensors. Now, if we're looking at the O2 sensor, air-fuel ratio sensors, that is to feed the cat. So if you're looking at it. So the O2 sensor will always be looking at information from the engine, how much oxygen is still left in the exhaust system. That's basically what it's looking at. So if there's a lot of oxygen, the voltage will be low. If there's less oxygen, which would be a rich system, voltage will be high. These things should be switching constantly. And you guys are looking into fuel trim, and we get into that. Short-term fuel trim should work with this. Now, the other thing we can use this for is open and closed loop. Because unless the O2 sensor and the short-term fuel trim are working together, we're in what? Closed loop. So we want to look at EGR diagnostics on some particular cars, catalyst efficiency by looking at the O2 sensors, the front and the rear, secondary air injection if it's working properly. If we are injecting air into the system, the voltage should go down. And if we look at evap for diagnosis, depending on the system. So a lot of these systems are looking at different sensors relationships. So you always got to keep that in mind. So if I look at that, those are the 6 primary inputs, and we're going to look at what happens when we start with an open loop system, a cold engine first. Okay, we're going to show you some live information from our trainer here. This is a J1850 OBD2 system, and OBD2 system, that's a protocol that we were showing you before. There's 2 protocols, pulse width modulated and variable pulse width. So we're looking at information here. So I have my ECM here. I have my throttle body, a mass airflow sensor, my diagnostic plugs down at the bottom. These are all the relays for the fans, the electric cooling fans, and the fuel pump is right here. I have an EGR, that would be an output, all right? I have my evap purge down here at the bottom. That's going to be also an output that would be duty cycled or turned straight on depending on the system. And we're looking at an evap vent. These are components here. On down here, I've got my injectors that we can use and watch what's going on. And I have ability over here to actually modify what I'm looking at in the process. So that's stuff that we're going to be looking at. So I'm going to start with OBD2 like I did before. So on this particular tool, if I'm looking at my scan tool, I'm just going to hit scan. And when I hit scan, you notice it says demo, HD demo, and we're going to look at EOBD or OBD2. Now the reason we do that is because if it's a European car, they go for the EOBD. That's across the world right now. So if I click on that one, it comes out and loads the software for this particular setup. The reason it's loading the software is because it's for that particular vehicle. It has to load it different. You got to keep in mind, different OEMs do their software a little bit different. So we're looking at what we've got right now, and we're looking at it again. And what you see is all the different protocols we can have. A lot of the techs or a lot of students coming out there, if you work on anything since 2008 and later, you're always going to be using the ISO CAN bus. Notice I went to the next one, I went down and I went to the J1850. That's with this tester up here. This is not an OBD, this is an OBD2 tester, but it's not a CAN tester, so it's a little bit of a process. And if you're doing your diagnostics and looking at stuff, one of the biggest things you want to do is make sure the VIN is there and it's correct. Some of your scan tools will not pull the VIN. That is mode 9, where we'll pull the VIN number up here. Notice we have readiness complete. All right, and if you look at readiness complete, and if you look at that, you have the readiness status. Readiness, if you don't know that, is the test that has run and whether it's completed or not. And then some of them are not supported, and it says data stream supported was 22 PIDs. So that's some information. If I hit more or hit enter, it says all the scan tools. I'm just going to hit enter on this one, and it brings me to the next menu. So I have my readiness monitors up here on the left-hand side at the top. I have read data. If I hit read data up here. Now, what a lot of the modern day scan tools are they're going to give you all the data for you to pick. And it's a good idea if you're picking data, you only pick the data that you really need, or you pick the minimum PIDs that you need in a vehicle. So if I'm looking at this system, I want to look at the mass airflow sensor. I'm going to look at engine RPM. I'm going to look at engine coolant. I'm going to look at absolute throttle. Depending on the system, there might be variations on that. I'm going to look at intake air, intake manifold pressure. So this one has both the MAP and the MAF. All right. And I'm going to raise this up a little bit, and I will have the ability to look at the oxygen sensors. But at this point, there's two oxygen sensors, one before and one after the CAT. So most of the time, we don't do a lot of that stuff on the one after the CAT, but there is some really good diagnostic processes there that we can use. So I'm going to hit OK. Now, right at this moment, you're looking at the data up here. Throttle position sensor is 0.392 grams per second. I'm going to ignore that one because the vehicle isn't running. What you will see a lot of scan tools do and a lot of cars will have a default value they stick in there. Now, out of curiosity, if I change the coolant temp sensor on this particular vehicle, did it change anything on that? No, it didn't do anything at all. So we're looking at it, but it did some other things. All right, it did change. It went down to, if you look at 69.8, if I turn this thing up a little bit, I'm at a different temperature. So when you first start up the vehicle, you want to make sure the temperature of the coolant temp sensor and the inlet air temp sensor match. So right now I got 69 and 32. So if I was doing this on a cold engine, I wouldn't have my degrees, but if I go intake air, now watch what happens. I've got 69.8. On a cold engine, I want those to be exactly the same. I want them to be within 10 degrees of each other so I can run my EVAP monitor. So that's data that you can use. Now, I'm going to set the fuel tables based up on the temperature, 69.8 degrees. I'm looking at my RPM intake manifold pressure says 13.2. Remember what I say, always use the rule of 2. So it tells my intake manifold pressure is 13.2. If I want to know inches of vacuum, that would be 26.4. Well, that would be atmospheric. So if we're looking at this data, if I turn around and let's start this vehicle up. So we're looking at some difference up here. All of a sudden now is live readings. Now if you look carefully, we'll see the RPM, the mass airflow sensor goes up. Watch what happens. Takes a little bit thing up here to get it, but there's my grams per second. Not changed as much because this is a demonstrator board, all right? But also, if you look, one other thing is I've got my temperature. They haven't varied any. If I will look at my coolant temp, watch what happens. Take my coolant temp, 120 degrees Celsius right now, all right? Celsius. So what happened to my coolant temp on this one? 248. That would be a hot engine. Well, back it down one to 100. 212 degrees. That's what it should be. You know, we're looking at it. So I'm looking at my intake air, right now 69. So I'm going to bring that up. And I'm going to do, let's say we'll leave it at about 104, 169, let's do 104. So if you look at it, my grams per second there, and if you look at my intake manifold pressure, now it's at 4.8. Well, if I wanted to know intake manifold in barometrics, what I told you, 8 to 12, I would times that times 2 and get my information. Now, let's look at, if I pull this back up, we've got our O2 sensors. And the O2 sensor right now is switching the one right above the bottom. The one at the bottom should be fixed most of the time when you're looking at it. If it's not fixed, you have an issue. So we're just basically looking data. Now, if I'm looking at the board, my O2 sensor on this little bar graph over here is going up and down. Notice it's going up and doing its job. Look at my rear O2 sensor, it's pretty well fixed. You usually want these things to go somewhere between under 200 millivolts and above 800 millivolts. I'm not always going above 800, but I'm there. Now, if I speed this thing up a little bit, when I speed it up, it went lean because we sucked air in it. Now, if I speed up a little bit more, the O2 sensor should change a little bit. Notice it doesn't do much changes on it. We got a little bit of an issue here. So that's a real quick way to look at the data on a cold engine versus it's warmed up. Now, if I do put this coolant temp at 120 degrees Celsius, which would be what? It's going to kick out to 248 degrees. Is that going to be too hot for the car to run? I would think so. We got an issue. If I take this thing and run it up, what happens? You see the RPM start to change a little bit, and we see some temperature changes. Again, the O2 sensor right now is working at idle. Off idle, it has a little bit of a problem. So we're looking at data across. Now, I could graph this, but I wanted you guys all to see this at the same point. All right, so we're doing this. This is the inputs we'd be looking at on the particular car. The next thing I'm going to do is set it up, and we're going to look at some of the outputs as we go across. The primary outputs are things we need just to get the car to go down the road. I don't really need an O2 sensor to drive it down the road, but I do need the idle air control. I need to be able to vary timing. I need to be able to have fuel being delivered to my system. I need to be able to, when I say fuel pump system, fuel delivery system, I need to be able to pulse my injectors to get fuel. I also have to have, on the cars that are equipped with an EGR, or variable valve timing, because most of the new performance vehicles have variable valve timing. There can be an EVAP system we have to look at. On all cars, we have an EVAP system. The other possibility we might have is injection, secondary air injection on a particular vehicle. That might be an output. It is an output that we might have to look at. So there's all kinds of things going in the car, but these are the main ones we're going to need. Now, fuel trim. Some people say fuel trim is an output. Some people say it's an input. If you remember what I said about the Chrysler speed density system and everything else, long-term fuel trim, as far as I'm concerned, is an input. Because I'm going to learn it, I'm going to input back in the computer. So whatever RPM level I'm at, whatever cell we're at, that's why I showed you those boxes before, the cells up there, I'm going to be able to modify the injection pulse width to compensate and bring the short-term fuel trim back to 0. So plus or minus 10 is what guys are always being used. Give you a little hint, a little tip here. If I'm at plus or minus 12, plus or minus 10, I'm okay. That would, if you had a drivability problem, that would indicate I probably got an ignition problem if I had a P300 code. If I'm above that, and I'm saying I'm at 15 or above, then I probably would be looking for a fuel problem. Lean condition, rich condition caused my issue. Again, using your fuel trim as a diagnostic tool. The other thing about it is, when we're doing this, short-term fuel trim should be plus or minus 5 to 10, and constantly switching in relationship to the O2 sensor. If the O2 sensor goes one direction, short-term fuel trim should go the other direction. It should always be doing that. So we have a possibility of everything working together. The other thing is we can have total fuel trim, which is when you add the short-term and long-term together. I tend to go to my Scantool and find the average of it, and I add those together. If I've got a lot of change up there, if I'm better than 15, I can have a drivability problem, and fuel trim will tell me I have a drivability problem without a code set. If I go over to look at idle air position, it's a percentage. And a good rule of thumb for you, if the counts are 25, 30, 40 or above, you've probably got a problem with the vehicle, and that problem would be something affecting the drivability, something like a cylinder problem, a pressure problem. Recently, I had a Dodge truck that I worked on, and the idle air control went to 40%. The command was there. The problem was I had a cracked valve seat on one of the cylinders, and I was seeing pulses on the intake manifold. It went up to try to compensate for that. On a speed density system, if it goes up, it adds fuel to try to compensate for issues. Mass airflow is a little bit different. If my idle air counts are 10 or below, that probably means I've got a vacuum leak somewhere. So you have to correlate this to the new a new throttle position sensor and a new drive-by-wire systems. It's a little bit different. We need to be able to look at some of the data sometimes because we have to clean the throttle body assembly. I've noticed there's a lot of codes and drivability issues right now with the throttle body assembly itself is carboned up, affecting this. That is really critical on the speed density systems because they have a volumetric efficiency chart based into the computer. If that volumetric efficiency chart's there, it thinks everything should be like it is, and we have carbon which affects it. It will affect the ability of the car to run real well going down the road. The other thing is PCV valves, the most not done anymore that I've ever seen. On older vehicles, we could remove the PCV valve, put a thumb over it, check the RPM vary, should be dropping 50 to 100 RPM to make sure it's working properly. The thing about it now, if your idle air counts are incorrect, there is a possibility, or your throttle body is incorrect, the possibility you have a PCV valve problem. The thing about right now is PCV valves are not easily removed, so they're not being addressed as much as they did before. So my suggestion for you is if you have a drivability problem, it's idle air control. Before you go any farther, check the PCV valve system, and on some of the European cars, you're going to replace the whole valve cover or the cam cover on the particular system. It's kind of neat to look at it. The other thing is primary outputs. It's going to be the injectors. I'm back from when they first came out with injectors, we had the throttle body, that's all we had. Then we went through the port fuel injector. Then we went to sequential fuel injection. And now we're at what? GDI. Now GDI is totally different than we've had before. So, because of GDI, we have increased pressure, so we're not going to have the pulse width we would normally see. I see a lot of GDI systems running at 0.5 milliseconds at idle, 0.3, under 1, and that's normal. When you rev the engine up on those particular vehicles, you might see an increase in pulse width, but when the pressure catches up, it'll drop back the other direction. At pulse width on injector, somewhere port fuel is somewhere between about 1.5 and 3.5 milliseconds. At idle, you snap the throttle on it, you're probably going to see 20 milliseconds on a pulse width on a port fuel injected car. But those are outputs you might want to look at as far as injectors. Again, without proper injection on the system, you've got a problem. Now, before we go any further, make sure you understand that if you have injector pulse width issues, you might be wanting to go back and look at the fuel trim per cylinder on some of them. If you work on European cars, you're going to have a smoothness or roughness test, and we'll give you some better idea of what's going on. Now, idle air count, I've already talked about this again. I've already given you information, but idle air count should be between 10 and 30 on the older ones. Fords are going to be in percentage, they're not going to be in counts. Chrysler and General Motors are going to be in counts. If it's high, look for carbon or something wrong with the mechanical on the engine. If it's low, look for a possible vacuum leak. Again, check the PCV valve. I will tell you again, if you take the PCV valve, put your thumb over it, pull it out of the valve cover, put your thumb over it, and you see a 50 to 150 RPM drop, the PC valve is working. If it doesn't drop, or it drops a lot, you either got the wrong PCV valve in there, or you have some other issues. If it doesn't drop, that means that we got a restricted PC valve, or the hose itself is restricted. Something to keep in mind on some of the older vehicles. As far as timing goes, you will look at my chart here. Timing should always advance with RPM. Now, I will give you another little hint. If I'm looking at my map sensor, or I've got a vacuum gauge on it, when I'm at idle, I should have 17 to 21 inches of vacuum around where we're at here, about 1,000 feet above sea level. If I go to 2,000 RPM and hold it there, I should have the same vacuum or more. The reason more, because I had a timing advance. So you can look at an issue there also. If I don't have proper timing advance, I won't get the increase in vacuum. This is something to keep in mind. If you have advanced timing, you have more vacuum. If you have retarded timing, you have less vacuum, and you also have a change in pressure in the intake manifold. It will change in the correlation. So there's something else you need to look at as going across. I wanted to look at something a little bit differently, and we're looking at injectors. I'm over on the circuit, and it says circuit history. In other words, this scan tool will check the circuit to see if there's a problem with the injector. So if I'm looking at one circuit history, it says okay, circuit injector status. What it would be if it had a problem with a wiring issue or a voltage issue or something else with the injector, it would actually say it's not there. So that's kind of neat. Now if I hit back on this one and go back and look, I just did 3. So again, that is under the misfire, or it's under the engine data there, and we did that. So that one you would find an output driver status. Now it's output driver status, so that's the outputs on the particular circuit. Those injectors, if I scroll up, evap solenoid, it's got the fan control, it's got the driver module status. If I go up here, fuel pump relay circuit status, let's do history, and let's do, let's just leave it alone for that one. We'll hit OK. When I hit OK, we're going to come out and we're going to look at some other information we might want to look at. In other words, we're looking at the outputs with the Scantool to see if it thinks everything's working properly. So right now it says the fuel pump status is OK and the circuit's OK. These are something, if the computer is doing its system, where it's doing comprehensive component monitor tests, it's checking the circuit out for continuity, it's checking out for voltage if it works. This is another way to see if we've ever had a problem with it, by looking at this particular data. So it's kind of neat that it's there. A lot of times, most of us play around with 4 or 5 different PIDs, and that's it. But you need to start looking at some other things in relationship. If I would have done evap, all right, you would have load speed, evap, fuel tank pressure. That's another sensor that on evap systems would be giving you a problem. I don't think we have a fuel tank pressure sensor on this one. But fuel level, engine load, fuel trim cell. If I did fuel trim cell, I don't know if that's even here, but if we do fuel trim cell, okay, it says it's in 0. Let's see if it changes. Okay, we did change cell to 2. On your vehicle, there is up to 20 cells that you might run into. The reason the cells are there is that's where it has learned the long-term fuel trim. So again, that's an input the computer used, but is being by the injector pulse width and everything else working. So that's something else to look at. Let's just look at one more thing here. Let's see if we've got, that's misfire data. If you look at misfire data, there's all kinds of information up there. You could look at current misfire data. Not all cars have that. We'll just do these up here, just do 3. So you would have misfire data on the system. And looking at it right now, I don't think we'll get anything out of it, but something you should do. If the vehicle has misfire data, you should check that. If not, you have to go to mode 6. And mode 6 is up there. It says right now you have no misfire, so we're okay. Another thing is, if you do mode 6, which one of these days we might do something on that one, mode 6 would have the last 10 drive cycles, the exponentially weighted moving average, or it would have the last drive cycle for misfires. Right now we have none, but if the car was missing, we should probably have a gauge up here. So quite a bit of information on your Scantool, but again, If the crankshaft sensor has a variation in it, it would indicate that we maybe have a misfire situation on the vehicle. So something you can look at for data. Anyway, that's pretty much what we've got. Okay, we're going to look at a few things that are outputs just to give you an idea what's going on. First thing I want to look at is an output would be my injector pulse width. And we also have an idle air control motor up here that we need to have that one. So we're going to look at data on the particular vehicle. So if we look at it automatically, I have engine speed, 678. Notice my idle air counts are at 54. If I was going, what we talked about before, 54 would indicate we might have a possible problem with this particular vehicle. I'm going to go ahead and put this in graph. That way we get most everything up there. So I'm looking at it, see what else we got at the bottom. Not much at the bottom of the process. So I'm looking at my startup. Now, one thing I wanted you to see is that at the bottom I have startup coolant temp and startup intake air. That is important. That way you know what you started with. I have my IAC counts. I have my injector pulse width at the upper right-hand side, and it's 2.8. Now, if I slowly open the throttle, goes lean a little bit, and then it should slowly increase. There we go. See the graph as it's going up because I am injecting more fuel. Now, if I was doing it, this one will not react to a quick snap, but if you were working on a car, you see a snap where it might go to might go about 20 milliseconds. So we're looking at that one. The other one, the spark advance, let's do that one. Lower right-hand side, you're at 28 degrees. If I rev the engine up, still stays at 26, depending on the cruise. So right now I'm at 29, 31, 38. You're seeing the spark advance going as I go faster. When I do a wide open throttle though, it's kind of funny. Spark advance will actually back off slightly. As it backs off slightly, the reason it does that is because I won't need as much advance on wide open throttle. Now, if you look at some of the other information, intake air, long-term fuel trim, is that an input or output? I'm going to say we have minus 16 up there. That would indicate to me that we have a problem probably with this vehicle that needs to be addressed. I'm at 13, 12. Now we're down to 11. So you want to be within 10. And as I sit down to let the idle go, it will come out as close as I can. Now, just to mess with this a little bit, change my fuel trim a little bit, and we're sitting at long term is 10, and my short term is changing a little bit differently. So if I'm looking at the process, guys, you can actually pick out one. We're just showing you some of the outputs you need to look at. The injector pulse width, if everything's working properly, should increase and it should follow the throttle, which it did. We're looking at the mass airflow sensor, that's an input. Spark advance should follow the throttle, which it does. So we know we got a good information. If I take the throttle position sensor down there and I rev it up again, you'll start seeing the injector pulse width kick up. This is a simulator, keep this in mind. And my timing. So we know that we have some things going on. So we have the input and output. Now we're doing a sensor simulator. This will be a little quicker if you're doing a live vehicle. But the fun thing about it is you need to test this to see if everything's working properly. If I have a spark knock on this particular system, I want to make sure that my knock sensor works. A knock sensor has to be there and has to retard timing when it happens. So that's one other thing we can look at. So right now, I would say this car is in bad shape. I got minus 30. If I put this put it back into auto here in a second, let it set there for a few seconds, and you should go back and start creating out there. If you're looking at the board over here, my O2 sensor is fixed lean right now. My rear O2 sensor is fixed lean. So what I'm going to be looking at fuel trim. Now, if you see it, it's starting to do its movement up and down. So it's starting to learn again. Now, if I'm looking at information, we're looking actually pretty good on this one. If I go across, we're still doing the data stream. So if you pick one up there. So gives you an idea of what's going on in the vehicle. And right now I'm almost fixed rich, so we know we have an issue. So this is just kind of showing you some inputs that we can use on this board to show you real quickly instead of going over a hood and have to manipulate the vehicle. This is open loop. We're looking at it, but the information I've given you so far might change your perspective of what you should be looking at. First of all, I can have a map or a MAP sensor. This one just shows a map. I'm not telling you what company I got this from, but it would have this data up here. What else is missing at this point in open loop? The other thing to keep in mind, we have long-term fuel trim that's related in open loop. The other thing that we're looking at that might be not here in the process is the battery. We need to know what the battery is in the process. So don't ever think that you don't have to check the battery in your charging system when you're doing drivability. We just shot a vehicle, we just shot a video talking about battery management, how to check the system. So that's something else, the relationship. If I go over to my next slide, we go into closed loop. We add the O2 sensor in there. Now, at this point, when we go into closed loop, we're also going to be adding short-term fuel trim in the system. So now we're going to have the O2 sensor being active, or the air-fuel ratio being active, and we're going to have a short-term fuel trim correction up there. So at this point, the O2 sensor is a fine-tuned device for the air-fuel mixture for the vehicle. Now, as a little bit of a fun thing up here, go to my next slide up here. At cranking and startup, we're going to have a little bit of an issue up here. So I went out and did this particular vehicle. And if you look at on this Scantool, on the upper right-hand side, they will say cranking fuel trim up there, basically. And so what I'm going to do is go ahead and play this video. And as you play the vehicle, you're going to see at this point, it automatically went cranking injector pulse width, went to 78. Boy, a lot. 78, what, 912? So if you're looking at it now, if I was looking at this data, that would only be during cranking. So what did I do? I used my intake air temp sensor. I used my engine coolant temp sensor, 40 degrees right now. My throttle position sensor is basically closed. My map value, I used my engine speed, my barometric pressure, and what else did I use? Intake air. And the coolant were what? Close together. So on this code engine, to start it up, I use the inputs that I was telling you for that would give me my fuel injector pulse width be increased. Now, the other thing is on a warm engine, you're not going to see the same thing. This happens to be on a warm engine. So when you're doing a warm engine, you're not going to get all those changes. But when you first start up the car, you're going to see injector pulse width be increased. You're going to see a timing change as you go across. If I rev the engine up, the timing should increase with speed. It should follow the map or the load sensors. So you're looking at a relationship with sensors. Get used to graphing some of this data out, and you'll get a lot better idea of what's going on. Okay, we're going to look at the board for a second. We're going to look at the car, or the Scantool information. What I want to look at, first of all, if you see the O2 sensors moving up and down with the bar graph up here, and that tells you that it's got the activity, but it doesn't really tell you how high it does and the average of it. Some of these Scantools will actually average the O2 sensor. Now, if I'm looking at the information, I've got that up there, I'm at RPM, everything else is looking good. I'm going to go over to my board and do that. Now I'm going to go over to my Scantool, and I have 678 RPM up there, but I'm looking at my O2 sensor. I need to go below 200 and above 800. All right, if you look at that one right now, if I just click that one, you're going to see my O2 sensor is going to flip out. Notice I have a 750 here on one side up here, and I'm going above the 750. My pattern's pretty uniform going across. They're doing it in blocks. Some of them put them in like a curve that you would see in an O2 sensor. But it gives me an idea that everything is working properly. I'm going from 0.82 to above 800 millivolts, and I've got a good running range. That's what you want to look at for the O2 sensor. Now, at the same time, if I looked at my injector pulse width, it should be constantly changing. It's not going to be a drastic change, but a slightly change. If it doesn't do that, we've got an issue with a particular car. So I'm looking at my injector pulse width. So in relationship, if I come down here and I look at, let's see if we look at a couple other things to look at on this one. I have other things up here to look at, and they're short-term fuel trim. Notice it's slightly changing. As long as the short-term fuel trim's right close to zero, it's going to go up and down and do its job. So right now, everything's looking fairly good. Notice there was an abrupt change right there as it went up higher. So we're doing a 0.781, which is within the range. If my long-term fuel trim is doing its job, let's go back to that. If I go to my long-term fuel trim, it's minus 4.66. What it's doing is taking away fuel slightly because the O2 sensor input and short-term fuel trim says it's slightly going too rich. What it's going to do is come back out, learn this correction. It's going to learn this correction and then adjust it every time it goes into this frame, this RPM, and this load. If I go back out again, I'm looking at other information. So again, my short-term fuel trim, my long-term fuel trim, my injector pulse width are all things that need to be checked and make sure it's working properly on the vehicle. Everything else seems to be looking fairly good on it. I've got a good idle speed. The only thing that I see I have a problem with the idle air counts right now is a little bit too high, which would indicate I would go back in and find out why it's there. It could be because it's running too rich and it's taking away fuel. So you have to look at all the data. So what I'm basically looking at is the long-term, short-term, and I'm looking at injector pulse width. So I am looking at the IPO. I'm watching what's inputs, I'm watching how they process it, and I'm watching the output. So again, the injector is an output. It's based off an O2 sensor and short-term fuel trim. So we're looking at, again, the information we need to determine if everything is working properly. Remember, I've got outputs and inputs on the same screen. So we can use the data together, and a lot of times it's better using graphs to get an idea of what's going on. So we'll look at something else now. I want to thank you for watching. Make sure you go around and check for any other videos out here that you might want to look at. Also look at the social media that we have. It gives you a lot more information what you might want to be looking at for if you're an instructor for classes coming up. So thanks for watching. We'll see you in the next one.